Good morning and welcome to today's webinar, Testing and Qualifying SSDs with a focus on 12 gig SAS interfaces. My name is Mike Micheletti. I'm a product manager here at Teledyne LaCroix, and I'm joined by Peter Lysak, who's an applications engineer. Looks like we have a good-sized group on the webinar with us, so that's a good sign. Looks like SSDs are high on everyone's Christmas list this year. Really what's been amazing is the pace of innovation in solid-state storage. Really in just a few short years, flash arrays have become mainstream in the data center. And adoption of 12 gig SAS is now in full swing. Thanks in part to all the new SSDs that are coming out. Finally, there are drives that can take advantage of the higher 12 gigabit throughput. Performance has been the main driver for SSD adoption, in particular with small random read operations. Using today's enterprise SAS SSDs, we're talking about read performance in the 1.2 gigabyte a second range, 145,000 IOPS, so an order of magnitude faster than hard drives today. As far as reliability, it's steadily improved with the emergence of these enterprise class drives. Because SSDs can wear out over time, vendors have added features to boost reliability, things like wear leveling and over-provisioning. This has allowed the industry to create different classes of SSDs for read and write intensive applications. SSDs are still more costly than hard drives, like 5 to 10x the cost per gig, but in terms of value, SSDs are considered to have lower cost per IOPS, so you can expect to see more SSDs in your future. There are a lot of other considerations when it comes to looking at SSDs, but for this webinar, we're going to be focusing on testing using SAS 3.0 SSDs. Peter will do a deep dive on 12 gig link training, giving us some insight on connection issues. We'll also look at some of the ways to test low-level functionality and error recovery, and then we'll talk about measuring and testing latency. So, by all means, please type in your questions using the question chat box. We'll try to cover any questions that come up at the end. And, of course, we'll send out the slides shortly after the presentation. So thanks for joining us again, and I'll hand it over to Peter.
Good day, everyone. So the main difference with the 12G drive from the previous generations, the Gen 4 to say 12G capable drives, is we now have back channel link training to ensure that we have a noise and jitter-free link at the 12G speed. From the SPL2, we're actually up to SPL3 now. This slide's a bit old, but the way the 12G training, back channel training is done is pretty much described pretty fully right in this one 5.10.4.2.6.3 paragraph. So I'm going to go ahead and read it here. So during the train TX speed negotiation window, SNW, after the local PHY and the attached PHY have both completed initialization, valid TTIUs and verified that the attached PHY is receiving valid TTIUs, the attached PHY's receiver begins training the local PHY's transmitter. The attached PHY's receiver may request that the local PHY's transmitter coefficients be A, held at the current value, B, set to a no equalization value, C, set to a reference 1 value, D, set to a reference 2 value, E, incremented, or F, decremented. The attached PHY's receiver increment or decrement request, the attached PHY's receiver only requests changes to a local PHY's transmitter coefficient if the local PHY's transmitter is indicating a status of ready on all the local PHY's transmitter coefficients. The local PHY's transmitter responds to the attached PHY's receiver request by adjusting the specified coefficient as requested. After the specified coefficient is adjusted, the local PHY's transmitter indicates the completion of the coefficient adjustment by indicating to the attached PHY's receiver a status of update complete, minimum, or maximum. That is, its minimum or maximum ranges have been reached. After the attached PHY's receiver requests one or more of the local PHY's transmitter coefficients to be updated, the attached PHY does not attempt to do analysis of a training pattern until after it has received a status of update complete, maximum or minimum for all the local PHY's transmitter coefficients that were updated. So that said, what's so special about this is that we have a brand new way to do this back channel training to make the link stable at 12G. And what this information unit is called, a TTIU for short, Transmitter Training Information Unit, is a 32-bit D-word, if you will, but it's not the same as normal traffic D-words. It's a 32-bit BMC coding scheme, but like other SAS or SCSI type commands, the field is a 32-bit field. You can see here we have a field for training and a field for status, each of which has several bytes of information that can, bits of information that can be conveyed. So those of you who have been reading the SAS spec for any length of time are probably familiar with these type of diagrams. In the first generation of SAS, SNW, speed negotiation window, we transmit align primitives at 1.5 G, and when our receiver says that we're happy with that, that we're getting good transmission, we move on and send the identify frames to have everyone introduce themselves and start regular communications. Moving up to Gen 2, 3G speed, we had a second speed negotiation window at the 3G speed, where again you start sending align 0 primitives and then indicate that you are happy by changing that to align 1 primitives, and that's the SNW2. SNW3 for the generation 3, we have what we call the PHY capabilities bits exchange. This is another 32 bits of information that's conveyed. This tells the initiator and target what they support, and consequently we set ourselves up with acknowledging of that. Formerly, with generation 1 and 2, the way you would tell that you don't support something is you just don't respond to it, basically. With SAS, of course, we always start negotiating at the very slowest speed and work up. So in SNW3, the original implementation for Gen 3, we said if we do support it, we support Gen 3, and whether or not we support spread spectrum clocking and that kind of thing. And then we go into sending train primitives, or the training sequence, which is a series of train primitives and scrambled zeros. And that's this area here, the train TXSNW to the right side. Formerly for Gen 3, all we did is we would send the train and the scrambled zeros for some length of time until we decided we were happy, and then we send train done primitives to indicate that we have a good link, and then we go on to normal communication. Now with the Gen 4, between these possibly several bursts of train primitives and scrambled zeros for the receiver training, we actually have this active back channel training. And that's indicated by the purple and dark blue areas interspersed there between the green, which is the train and train pattern, and the scrambled zeros. Whole bunch of acronyms here that I can never remember, so I thought I'd just throw in this next slide where they are all defined for us. The RCDT, SNTT, SNLT, SNWT, etc. And Mike will touch on a couple of these when he covers our SAS verification test suite. So I've been working in the storage industry for some time now, here at LaCroix for about 6 years. As far as the decode of SAS, well, once you have linked up at 12G, it looks pretty much like it did at 1.5, 3, and 6. But the big real difference here is this 12G back channel training sequence. And the Teledyne LaCroix Analyzer, we have concentrated on this facet, I think, with a lot of effort to make sure that we have a very good decode for this activity. So in this slide here, at the top, we can see the end of the PHY capability bits exchange, and then we launch into our first 12G training receiver and transmitter training sequence. You might note there that the analyzer decodes the PHY capabilities bits exchange as COM-wake, because that's what it looks like to the analyzer. But here I just took a recording of a link-up sequence and then went to our search feature, click on the binoculars from the toolbar, and then scroll down, and we can go right to the beginning of the training sequence by just clicking on training sequence and find next and don't care. So here's the beginning of it. You might note the couple of red protocol error packets there. That is whenever there's a speed change, a marked speed change, the analyzer will lose lock for a D word or two, and that's what those are. So this training sequence can go on for quite some time. As we said in the previous slide, the whole the whole thing has to complete within 500 milliseconds. But in that time, you could actually go through the entire sequence several times. It generally only takes a fraction of that to go through a complete sequence. But these TTIU transmission, each side keeps transmitting the same thing over and over again until the other side, for its status, says, "I've received your data, and then then I'm ready for you to do the next thing." So generally, the way our decode shows it, this packet here is many actual transmissions of this 32-bit pattern over and over again. And if you look at the far end field, you can see for link 711 a count of 547. That means that 32-bit pattern was transmitted 547 times before the transmitter got word from the other side that we can move on from there. What I've done here, when we ordinarily, if I go back, these green training sequence packets are collapsed is the default, but then if we open them up, we have a lot of information contained in them. So you can see we have a decode for all 32 bits basically, and then this metrics, we keep a tally of how far we've incremented or decremented and how many total TTIUs have been transferred during this training sequence. So what I've done here, going back to our search menu, training sequence, click on the Advanced button, and this control status dialog pops up. And if I check train complete and push the Find Next, that will cut to the end of the training sequence essentially. And then if we look at the metrics at this point, you can see they're in link 3297. We can see in this sequence 144,059 TTIUs were transmitted from the. I used actually a 2-meter cable when I made this recording, and so you can see there were some major adjustments to the coefficients, and then you can see we have the completion time of 17.667 milliseconds. And if we just scroll down a bit, this is a slide, so I can't do it. Right below this, we would go into the standard training where we're sending train primitives and the series of scrambled zeros to train our transmitters. So through this slide in here, this is also from the SPL2 and SPL3 specifications. I'm not sure if this makes it easier to understand how this should be done or not, but this is how the people who wrote the specification show how the correspondence between the receiver and the transmitter should go about to hold or decrement or increment to get the best possible I. Some testing tips. So Teledyne and Croy, we have two 12G capable analyzers, the 2-port Sierra M 12.2, the last 2 standing for the number of ports available, and the Sierra M12.4 or 124, which was our original 12G product, has 4 ports, and so it services all 4 links of a standard mini SAS HD connector. I didn't put any slides in about this, but I'll touch upon it, that the Sierra M12.2 and M12.4, the front end was specifically designed to be as uninvasive as possible, so that the host and target can train naturally among themselves, and we just sniff what's going on. So the actual training that is in the trace is really the training that's going on between the initiator and the target, and we are just recording the traffic. When you do invoke our jammer feature or our trainer, our traffic generator tool, well, then we have to become an active participant, and the jammer actually has to train both to the initiator and the target, and the trainer could act as either the initiator or the target, and it will do its own 12G training to achieve a link. And this is entirely separate from the actual tuning that we do to get a good clean capture in the analyzer. So my second bullet point here, the analyzer should use auto-calibration to remove RX errors. Well, that primarily refers to our tuning between the signal that we are sniffing and to make sure that we have a good clean capture. And we have an auto-calibration feature. We have the first one, it's just an auto-calibration button. You push the button, and chances are it will clean up the signal nicely for you. If that does not clean it up well, we have an advanced auto-calibration feature, which can take some time to complete, that should arrive at the very best possible eye. And then I guess I'm kind of reiterating here the last point here. The jammer or trainer may require manual calibration. We do have algorithms built into them to get to the best eye, but sometimes devices will ask for references that makes it very difficult to train to a good sweet spot. And then when this occurs, we might have to manually put in a starting reference value. And with that, Mike will continue to discuss our SAS verification test suite.
Okay. Great. So I think you can tell link initialization is a little more complex when you're operating at 12 gigabit. But what about the higher layers at the protocol layer? So SAS 3 is very similar to SAS 2, a lot of the same state machines, same timers, but now we're running twice as fast. So your storage system OEMs, your server OEMs, they're looking for tools that can help them screen these 12 gig devices to ensure they're compliant with the SAS spec. So UNH, University of New Hampshire, they have their interoperability lab, and they publish a test spec for doing just that, for testing if a device is conformant with the SAS standard. The test spec is supported by our Teledyne LaCroix Sierra M124, which has a traffic generator option that can be used for this kind of testing. So it can emulate a real host and transmit specific traffic conditions to a target. The verification suite has been available for 6 gig SAS for some time, and now it's available for 12. The idea is that now you have a framework for testing speed negotiation, link, transport, application layer behaviors, and it's fully automated. So the SAS verification suite is actually integrated into the Analyzer software. There's a short video here that will kind of give you an idea how this works. So you select SAS verification. It will really just bring up a console that allows you to pick which tests to run. First, you'll specify the connection rate. So it can support 3, 6, or 12. And then in the video here, we'll pick a few tests and then run them in real time. We'll come back and look at some of the specifics of these individual tests. Again, the tests themselves are organized by logical layers of the spec. There are speed negotiation tests that are considered part of the PHY layer. There are tests that focus on the link layer, the transport layer. So we're specifically testing different assertions within each layer. So using the Add button, that moves the tests over and into sort of a queue, and you press the Start button, and from here, it's fully automated. It's going to load the script, arm the analyzer, run the test. The analyzer captures the response from the DUT and then automatically determines if it's a pass or fail. All your traces are saved, and at the end, a report is generated. So again, fully hands-off, and one of the only solutions that can test at 12 gigabit. So let's look at a couple of these individual tests. This is 5.713, which verifies one of the timing windows for the speed negotiation process. 12 gig SSDs must support the SNW3, like Peter mentioned, and that requires that PHY capabilities bits are exchanged between the two link partners. So these are low-level 32-bit messages. They're sent at the end of SNW3, but they're actually embedded in a series of COM-wake patterns. So the two sides are communicating by sending out-of-band COM-wake messages. There's a predefined window of quiescent time that must be observed after the series of COM-wakes. Again, both the link partners must stay in OOB idle for this interval. It's 562 microseconds. After that last COM-wake signal, they need to wait for the other side to basically decode its bits, its capabilities, set the registers, and just get ready for 12 gig operation. So we have a test, of course, that validates these different timing intervals. This is what it looks like on the bus. So this is a screenshot from a real test, and actually a trace, right, from our SAS verification suite. We see here there's a traditional packet view at the top, and then there's sort of a waveform view at the bottom. The measurement is from the last COM-wake to the first 12 gig D word from the DUT. So using the quick timing markers, we can easily do this kind of packet-to-packet measurement. Again, we're looking at this interval between the COM-wake and when the target starts sending training. So that's the first 12 gig patterns on the bus. And this shows that it's 564 microseconds of idle. So the device would pass. You know, it's a simple measurement. You could easily do this manually, but having an automated test harness that can systematically test, you know, new SSDs or new firmware as it comes in, you know, that can be a time saver. Okay, another example, testing the credit timers. So SAS uses R-ready primitives to flow control data into the device. Flow control is pretty important with SSDs because it's one of the mechanisms that the device can use to pause the inbound data. Again, SSDs are going to use flow control when it's busy doing background tasks and it can't accept more data. So in the test 618, we verify that a device will properly observe credit timeouts, which is part of the flow control protocol. You know, if the initiator withholds credit, does the device properly respond? So again, here we're looking at our spreadsheet view where we show initiator and target traffic in separate columns. It starts with the initiator sending an inquiry. The DUT acts the command. It sends an SSP open in order to return the inquiry string. The initiator sends the open accept, but then it doesn't issue an REady. After 1 millisecond, the DUT correctly sends the done credit timeout. So this test is officially over at this point, and most devices are going to just retry by sending another open, try to reopen a connection. And actually, we see the second attempt here in the test. The initiator here still is not sending any REadies, so after 1 millisecond, the device issues a break, which basically cancels the transaction. And now the command has to be resent. So this just gives you an idea of the sequence that we're testing, and there's several different sequences that are going to be tested in each of these tests. Another example, 6.111, which tests the ACNAC timeout with interlock frames. So in a nutshell, when you send an interlock frame, you need to receive an acknowledgement before you can transmit the next packet. So interlock frames include your command, your transfer ready, your response frames. In this test, we again start by sending an inquiry command. The DUT acts the command, then sends an SSP open in order to reply to the inquiry. The initiator sends an open accept. The DUT sends the response, but the tester doesn't act the response. So the proper behavior is that after 1 millisecond, the DUT correctly will send a done ACNAC timeout, and that would complete the test. So this is a specific test for ensuring that primitive gets sent. But how does the device actually recover from an ACNAC timeout? Well, that's verified by one of the Chapter 8 tests, because retry behavior for SSP frames is performed at the transport layer. So that's tested in another clause, actually in the 8.1.19 test. Again, similar sequence. The host sends an inquiry. The SSD sends a response. The tester withholds the acknowledgement, just like we did previously. We get the ACNAC timeout. The DUT is supposed to open another connection and retransmit the same response frame. So the software is supposed to verify that it does, in fact, resend the frame with the same tag and the retransmit bit set to 1. So again, the ACK from the initiator completes the transaction, and that's basically how recovery is done on an ACNAC timeout. So that's a few examples of SAS verification. Again, it's mostly focused on handshaking timeouts and error recovery, but it's useful as a first-pass screening tool. There's really, again, no other system out there that can do this kind of testing at 12 gigabit with a real device. Okay, so performance testing for SSDs is a huge topic, and of course it's very dependent on the application or the workload that you're targeting. As far as testing a single target, probably nothing is more relevant than drive latency, which we define as the time from command to first data. And with write performance in particular, that's a focal point, again, because of how SSDs write data to disks in blocks. Again, even a small write operation will consume an entire block. So it's necessary to periodically reclaim the unused blocks by reading, writing, and then erasing these partially used areas on the drive. So this process is called garbage collection, where you're consolidating the unused blocks. When this is going on, it can delay normal I/O because the drive's going to be busy, right? So SSD vendors have done a lot of things to try to mitigate this, but latency is still the main symptom of this problem, and this still is the main issue they're trying to combat. The issue tends to get worse as a drive ages, right, as it starts to fill up. So we'll look at how you can analyze latency, and we'll look at maybe some of the command queuing and how that can actually have an impact on latency. Okay, so right here we're looking at a high bandwidth trace between real devices. So this is real world traffic, real host, real device, and we're basically showing the SCSI command layer. There are multiple SCSI write commands in this screen. And these are line rate captures, right, with the analyzer. So to measure latency in a trace like this, you could obviously look at each transaction and manually calculate the latency, packet to packet, command to data. But we also have several tools that can help you here. VSE, or Verification Script Engine, it's a scripting language for automating routine tasks. It's an API, really, for extracting data out of a trace. And kind of give you a quick flavor of it, I have another kind of short video. The button on the right opens this VSE console where you can run individual scripts. There are several examples already in here. And we actually have a script for measuring latency. The edit button opens a script. You can see the syntax. So it's very high level, fully documented. You can create your own. Obviously, now I hit the run button, and this script is automatically going to calculate latency for every command in the trace. It shows the min, max, and average, and we see the max latency there, almost 8 milliseconds on that worst case command. So this is all done with a script, in an automated way, and that obviously can save you a lot of time. So now I want to investigate a little further what's the root cause of this specific command. I'll jump to that command. I guess it's 20,094. It's a write 10, of course. We often see higher latency on writes. If I open the command, we can see all the individual transactions that make up the specific write 10. Of course, to verify latency, you can measure the command to first data, right? Command to first data is the latency measurement we're doing here. But what's more relevant is command to transfer ready, because that tells you if the latency is due to the host or the device. Was it the SSD waiting for data from the host, or was it the other way around? So using our quick measurements markers, we can put an X on the command and put a Y on the transfer ready. And you see this interval is 7.89 milliseconds. So the drive seems to take a long time to send the ready-to-receive packet. Virtually all the latency is waiting for the drive to send the transfer ready. And this is pretty significant. It's about 100 times the average latency for this device. So how can we, drill down and try to identify the root cause? Again, that's again above average latency, but you could certainly see higher latencies with some devices. Okay, so command queuing is in effect with SSDs. Again, it was primarily designed for hard drives, but it is used with SSDs. Because of the seek time, it's more relevant for hard drives. The analyzer software actually generates a series of bus utilization graphs, and this one I'm showing here actually shows your pending SCSI IOs at the same point in the trace, right at the same command. So right away you notice that the queue depth seems to be very steady at 3 or 4 pending commands, and then it kind of jumps to 9 at our max latency write command. So is it the command queuing that's causing this spike? If the drive is serving other pending commands, you may see an increase in latency. So this can happen, but you wouldn't see a gap like this where the queue doesn't move. I mean, it seems like it's really frozen. There are no commands getting completed at all during this interval. So that wouldn't be consistent with commands getting queued up in the background. So the true root cause can actually be seen using our power tracker display. This is actually a plug-in card that is available as an option for the Sierra Analyzer. It provides a histogram of power consumption. It's synchronized to the trace, so you can see the correlation between what was occurring on the bus and what was occurring at the power level on the drive itself. Again, only measures a single power at a single target. but you can correlate it to transactions on the bus. And what we see is a spike in power consumption at the same point in the trace. And this is a telltale sign of garbage collection in SSDs. And really, it's one of the only ways to identify when this kind of background reclamation is going on. That is to monitor the power draw, because there's additional circuitry that's getting powered up when it's doing garbage collection. But it's all internal to the drive. So clearly, this is a case where you can identify when this garbage collection is going on, and not all firmware is created equally, right? You know, some of this optimizations can clearly cause latency spikes, and having tools on hand that can help you find and measure these issues is pretty important. Okay, so to summarize, with 12 gig SAS SSDs, you're really going to face, you know, most of the same issues, whether you're testing hard drives or solid state drives. Again, at the electrical SAS layer, they look very similar. Again, you'll need to have an understanding of link initialization and speed negotiation, so you can debug those issues as they come up. For the protocol layer, there are automated tools available for 12 gigs, so that's one way to increase your confidence in your SSD components. Regarding performance, there are a number of software and freeware tools that can be used to test SSD performance. Most of you are probably familiar with those. Again, things like Atto and Iometer. Again, tools that let you customize the block size and the queue depth are pretty important, because you really need to do performance testing for your specific application. And of course, you may also need an analyzer to figure out what's causing these performance issues. So, you know, things to consider. Okay, so that kind of completes the formal material we wanted to present today. And so, again, we're certainly interested in answering any questions that may come up. And so let me see if I can determine if we have any. Okay, one of the attendees writes, how long does it take for a typical drive to power up the recovery for the training sequence? How long does it take for a typical drive to power up the and get ready for the training sequence? Let's see. So, you know, again, if it comes to SSDs, you're obviously looking at less latency when it comes to the spin-up time, because there is no spin-up. And so that is something that you won't have to deal with. But Peter, do you have any experience on this specific question?
I think yeah, what can be, you can certainly use the analyzer to see when you're getting traffic, when both the initiator and the target first start communicating. Ordinarily, as soon as power is applied to the drive and it receives a COM SAS OOB burst, it will respond in kind and start the link up procedure. If we go back to some of the slides we showed, there are some timings that you are supposed to be compliant with as far as when linking first begins, that you are to stay inside those windows. And then when you get to the 12G training sequence, you have your 500 millisecond window. Yeah. Kind of going further with that, we have another question. How can we tell if 12G training has failed? There's a couple of pretty easy ways you can see that with the analyzer. First of all would be that we always in all of our views we give an indication of what is the link speed, the current link speed of the traffic, right at the edge on the left-hand margin. We'll tell you if you're at 6G or 12G. The 12G training sequence and the 6G training sequence actually look identical at the end, where we have the train and the train done and the scrambled zero primitives being sent back and forth. But it looks identical, but the analyzer will tell you that what speed those are being sent at. And of course, if you see they're at 6, we know we must have timed out and dropped down to 6G speed.
Okay, great. So another question from one of the audience: is there any benefit to using 6 gig SAS SSDs with a 12 gig host? And yes, of course, 6 gig target devices would be backward compatible with 12 gig. Again, and if you're using a 12 gig expander on the other side of that backplane, and it should use multiplexing to actually provide the full 12 gigabit bandwidth upstream to the host initiator, right? And yes, I mean, again, this is a rate matching feature, and some of the early expanders didn't support rate matching at the multiplexed rate, right? And so the more recent modern SAS 2 and SAS 3 expanders seem to have implemented this better, and you actually do get higher bandwidth if you're using 6 gig devices on a 12 gig logical link. Okay. Question about whether we can test initiators with the SAS verification suite, and we currently cannot. So it's a good question and something we'd like to add. It is definitely more difficult to emulate a target port and talk to a host and do these kinds of tests because we're not the master. But we're looking at ways to do that. They are part of this test spec, and so we hope to get there someday. Okay, and someone has written that this is an issue with one SSD vendor, that it was taking a long time for the drive to come up to speed, so that was affecting the passing of the LaCroix SAS verification testing. I see. Yeah. So that is something that we've seen as well in we have a SATA compliance package that uses some of the same sort of implementation, and we've actually added a customizable delay between each test just for that reason. And so that's something that we probably will need to add to the SAS compliance suite, because again, some of these devices do take longer to become ready, doing their own housekeeping before they are ready to operate at 12 gig. So thanks for that input. We will try to make some improvements for those different devices. Fortunately, 12 gig devices are much more available now, and I'm sure most of the audience is finding they can actually access production level devices, and that's making giving us a lot more things to test, and there's more on the way. So that should keep everybody busy out there. And we've just about come up on our 1 hour mark. So with that, I will thank everyone for joining us. And again, if you have additional questions, please send them in. We'll be happy to try to answer any questions after the event. And of course, you should all receive an email with access to the PowerPoint slides so you can review these if you wish. Again, look forward to more webinars from Teledyne LaCroix, and thanks again for joining.